Okay, this is about Surds, a GCSE topic, um, but also about irrational numbers. And there's a little bit of confusion, I think, in this area. So I think the first thing we'll do is we'll just get a little bit of terminology sorted out. So let's just read from this. Surds can be a square root, cube root, or other root, and are used when detailed accuracy is required. For example, the square root of 3 and the cube root of 2 are both surds, and the square root of 5 is a surd square root. So this will be this is a surd here. And incidentally, if we have a result that involves the square root of 5 and we're asked to express the square root of anything or the cube root of anything, we're asked to express it exactly, then this may be the only way that we can express it exactly. So actually putting in your calculator and working out a decimal to so many places is not an exact solution. So we may have to write this as part of the solution. Now that's that. Now what's an irrational number? Now an irrational number is a number that cannot be written as a fraction or a ratio of two integers. Irrational numbers have decimals that can go on forever without repeating itself. So we've got an example in pi, which of course is the ratio of the circumference of a circle to its diameter. Now this square root of 5 is an irrational number. So you can see we've already sort of encountered a little bit of confusion on this. So really, this sort of topic is really about irrational numbers that involve square roots, cube roots, and so on, that won't resolve directly. So it's obviously the square root of 64 is 8, so that's going to be a rational number. But these square root of 5, stick it in the calculator, you just get an infinite number of decimal places. So what we're talking about are irrational numbers that involve a surd, really, and they're sometimes called surds, but it's surd is only part of it. And here we've got an example here: 3 plus 2 root 5. And so in this case, actually, what we've done is we've taken our square root of 5, which is, as we say, is irrational, and if we scale it, in this case multiply by 2, that is scaling it, and then shifting it, we've added 3, so that's what we mean by scaling and shifting. Then that number is still irrational. Okay, so really this topic is, generally speaking, about these sort of expressions and manipulating these expressions. So we're not just talking about manipulating square root of 5, for example, or manipulating pi, both of which are irrational numbers. We're talking about things of this form, where this constant out front here may be 0. This constant here, which is a multiplier, may be 1. But in general, it's of this form. Okay, so I hope that has clarified a little bit. Anyway, let's just go on and think of another couple of concepts here. We talk about the conjugate of an irrational number. It's a non-zero number such the product of the two numbers is rational. So, for instance, 3 plus 2 root 5, we take 3 plus 2 root 5 and multiply by 3 minus 2 root 5, then we end up with a real number. We'll look at examples of this in a moment. Okay, so they're conjugates of each other. So you could say that 3 minus 2 root 5 is the conjugate of 3 plus 2 root 5, and vice versa. In actual fact, they're sort of conjugates of each other. All right, so that is one important concept that we need to understand, and we will use in resolving problems around this. Two numbers are only equal. Two numbers, irrational numbers, it should say, of the four if of the form a plus b root c, or possibly that d plus e root f. They're only equal if A equals D, B equals E, and C equals F. Okay, so all those things have got to be true, which is actually quite useful when we're solving problems involving numbers of this form. Okay, so text has got a bit mixed up there, but that's what we're talking about. By convention, we do not leave irrational numbers as a denominator. So sometimes we may well see numbers of this form as either a numerator or a denominator or both. But by convention, we don't leave the number in this form on the denominator, and we can always, by using conjugates, we can always turn the denominator into a rational number, although that will generally leave the numerator as irrational. Okay, so a few concepts there. If you just need to go back over that, then that's fine. But I think it probably come a bit clearer when we look at some examples. So let's just go through these examples here. All right, so simplify the square root of 32 plus the square root of 98. Okay, well, let's just look at each of these in turn, because square root of 32, well, we can just break this up under the square root sign. And the key thing here is that this 16 times 2, or square root of 16 times 2, is basically equal to the square root of 16 times the square root of 2. So this, I often teach this as being, this is your bus shelter. And, if we've got two numbers multiplied together here, then we can give them each number its own bus shelter. And conversely, of course, if we've got this, we can actually put them under the same bus shelter. So so that is one of the important concepts. Now, if we look at this, of course, square root of 16 is 4. In some contexts, we might want to say, think about the negative square root, which is -4. But I think for the purpose of these problems, then let's just think about the positive square root at the moment. So this is, and so that's 4 times root 2, and we write that as 4 root 2. Similarly, 98 splits into 49 times 2, and giving them separate bus shelters, of course, like this. We can write it like that. Square root of 49 is 7, so that's 7 root 2. So when we look at the sum of these two things, square root of 32 and square root of 98, we've got 4 root 2 plus 7 root 2. Now, we can add these because this is like 4 apples plus 7 apples, or 4x plus 7x, or whatever. And so simply we can write this solution as 11 root 2. Okay, so that is that. And this sort of bus shelter idea might be a silly notion to you, but it helps some people. Actually enables us to do that. Right, let's have a look at this one. Express 6 divided by root 2 in the form a root b, where a and b are positive integers. Right, okay, this is an example where, yeah, we don't like irrational numbers on or numbers of the form a plus b root c on the denominator. And what do we do? Well, we need to do something to turn this into a rational number, and the easiest thing to do is to multiply it by square root of 2. And of course, if we do that to the denominator, we must do it to the numerator. So that's what we're doing here. And then follow the bus shelter rule here. We've got 6 root 2 divided by the square root of 2 times 2, square root of 4, which is 2. 6 root 2 divided by 2 is equal to 3 root 2. Okay, so that is an illustration of what we're talking about there. We've got another one here. Rationalize the denominator. Okay, of 1 divided by square root of 2 plus 1, 1 over square root of 2 plus 1. Sort of rewritten it like that because it helps. Now we're going to use the conjugates here because, as I've just said, if we multiply the denominator by its conjugate, then we're going to get a rational number on the denominator. But of course, if we multiply the denominator by a rational number, we've got to multiply the numerator by the same thing, by an irrational number. We've got to multiply the numerator by the same thing. So the numerator becomes 1 minus root 2. And on the denominator, well, we're going to get our 1 times our 1. Now we've got to get this, the inside ones here and the outside ones there, they're actually going to cancel. That's going to be minus 1 times root 2 plus 1 times root 2. So they're going to drop out. Plus, oh, sorry, I should say minus root 2 times root 2. Minus, so minus there. Okay. And that simplifies, since these terms drop out, that's 1 minus 2, the product of root 2 and root 2. Okay, so that's going to give us 1 minus root 2 on the numerator and 1 minus 2 on the denominator. Okay, so that's just minus 1. Then we just switch the signs around because we've got multiplied by minus 1 on the numerator and denominator. And that's going to leave us with this root 2 minus 1. Okay, so that's that. Let's have a look at this one. Expand and simplify this. All right, so yeah, kind of relatively straightforward, just doing similar to what we've done before here. So I've drawn my face in here. You might not have done it like this before, but if when we're multiplying a bracket of 2 items with a bracket of 2 items, then we draw in the eyebrows and the mouth and the chin, then basically this connects up all the possible combinations of things that we need to multiply. Oh, it looks a bit like it now. Look, there's a couple of eyes there and a couple of ears here. Yeah. Okay, so this one here is 2 times 7. That's what we got there. The left eyebrow would be root 3 times minus root 3. And then we've got the mouth, 7 root 3, 7 times root 3 there. And the chin is going to be 2 times minus root 3, or minus 2 times 3. So we've got that. Okay, so grouping like terms, that gives us 14 minus 3 times root 3, minus root 3 times root 3 is going to be 3. And then we've got 7 root 3 minus 2 root 3. Okay, so 14 minus 11 is 3 is 11. 7 root 3 minus 2 root 3 is 5 root 3. So that is the simplified expansion of this expression here. Okay, so that's another example, and it's sort of typical kind of question. Another one here, expand and simplify this. Now this sometimes we can simplify these things using other rules, and this actually, if you recognize the difference of 2 squares, then this one fits into that pattern. So the difference of 2 squares, so if we've got for instance we've got x squared minus y squared, let's just write it down here, x squared minus y squared is equal to x plus y times x minus y. And again, there's sort of the insides, the xy and the minus xy are going to cancel each other out. So we can think of this first bit as our x, this second bit as our y, and rewrite it like this. So this is your x plus y times x minus y. Without just going through all the calculations in detail, I think we can simplify this. In fact, this left-hand bracket, you can see, becomes 4, doesn't it? 2 plus 2, and then the plus 3 and minus 3. So that becomes 4. and then multiply and then do similar to the right hand, and we get 4 into 4 minus 3 is equal to 4. So yeah, so the other things that can make it simpler. I mean, you could just multiply this out, multiply that out, and then subtract them. Another way of doing it. Right, final example. Show that 5 plus 2 root 3 over 2 plus root 3 can be written as this. Yeah, well, same thing really. We're looking at this irrational denominator. And so we're going to multiply it by its conjugate, and then we're going to do the same thing to the numerator. We can draw our face out. It's a bit more difficult, obviously, when we've got more terms to worry about. But you don't need to do that, really. 2 lefts, this is a 5 times 2, the insides, the outsides, and then 2 rights give us what's on the numerator here. Same thing for the denominator, although we know that the 2 times minus root 3 and the root 3 times 2 are going to cancel each other out. So we're left with this on the denominator, 4 minus root 3 times root 3, which of course is 3. So 4 minus 3 makes 1. That's what we've got there. And simplifying the numerator, 4 minus root 3. So 4 minus root 3 divided by 1 is that, and that is what we have been asked to show. Okay, so hopefully it's a little bit of terminology confusion that I'm hoping I've clarified for you. Just what is a surd, what is an irrational number, but what are the questions about? It's something which actually is kind of a bit of a combination of the two. Numbers of a form a plus or minus b root c, and that root could be a square root or a cube root or whatever. So so that's it. And in order to solve these, we use the ideas of conjugates, bus shelters, and so on. Okay, so there've been more worked examples on this, but hopefully that's kind of given you the idea. And okay, so I will see you next time.